Today we're going to simulate a 5-volt, 1 amp buck converter using LTSpice and are going to explain the functionality of each pin on this LT8631 switcher IC and explain how to calculate all the passives around the switcher IC. Hey everyone, welcome to another episode of Electronic Savvy. Today we're going to take the same circuit that we calculated and explained last week, and we're going to simulate this buck converter using LTSpice. This switcher IC steps down a typical 12-volt supply into a 5-volt, and it can source up to 1 amp of current. So as you can see, this switcher IC has a couple pins. It has enable, it has VN, it has internal regulator, and a couple other things that we're going to go through in just a sec. But I just want you guys to understand that this is a simplified version of the chip. And in the next episode, we're going to take this same IC and we're going to actually build the board. Like, we're going to do the layout in Altium and we're going to do the board. So it's always good to model your circuit, simulate your circuit before moving it to layout, just to give you an extra level of certainty that this design actually does work. So it's always good to kind of play around with some of the passive values and how does, for example, changing the step on the output load will change the performance of your switcher IC. So I really recommend you guys simulate your switcher ICs before designing an actual PCB. Basically, what we're having here is we have an enable pin, which is simply just you can think of it as a switch where if this enable pin is pulled high, which in this case is, this switcher IC will be on all the time, but if it's pulled low, it will always be low. So usually, if we're not using any microcontroller, just connecting it directly to the high side, to this high voltage, this ensures that this IC will always be on when there is a supply. And the other pin is VN, which is simple. It's just your supply source. It's your supply voltage. And the other pin is this internal VCC, which is basically it's just INTVcc, just internal voltage regulator, which is a 3-volt regulator that this IC uses for all the internal processes and all the controls. And then we have this bootstrap capacitor, and then the switch. So bootstrap capacitor, the reason that we're using a bootstrap capacitor is this switcher IC is a synchronous converter, as we discussed in the last video. Synchronous converters basically are the converters that use a high side and low side switch, and they do not use any rectifier or any Schottky diode. So they're much more efficient than asynchronous converters, as we discussed. But there is a small downside when we use a synchronous converter, because there are high side and low side N-channel MOSFETs. We'll have to use a bootstrap capacitor. As you guys recall, I explained the exact reasoning in my last video, but just to touch on it really quickly, for a low side switch, we can use N-channel MOSFET with no problem because the gate of that MOSFET will always be higher than the source. So that would be fine. But for the high side switch, because the switch node in this case is basically connected to the source of the high side switch, we need to provide higher than the source voltage at the gate of this high side switch. And in order to provide that extra bump in voltage, we need to use this bootstrap capacitor, which enables the high side switch to turn on and stay on robustly. So that's why anytime that you use a N-channel high side switch, you must use a bootstrap capacitor in order to give you that extra potential on the gate that enables the gate voltage to be higher than the source voltage. And then here we have the switch node, which is basically just a switch node, as we discussed it in the typical converter, buck converter. We have that switch node, and then which connects directly to the inductor. And then this inductor pin, this IND pin, is basically connected to an internal sense resistor inside the chip, which is used to regulate the output voltage. And you may be curious, why is this inductor node in here? Well, the reason is this particular switcher uses current mode control to controlling the output voltage of this buck converter. And then here, obviously, we have the VOUT and then the feedback pin for setting this output voltage. In this case, again, we have the equations, which is pretty straightforward. You can find it also in the data sheet. Following this equation, I found the values for the feedback resistor in order to give us exactly 5 volts on the output. And then here we have this output capacitor, which helps with the output voltage ripple. And depending on how little of ripple we would like to maintain the output voltage as, we need to use a higher capacitance. So in this case, 47 microfarad is recommended by the data sheet, and the larger the capacitance, the smaller the output ripple gets. And similar thing applies in the inductor. And the larger the inductance, the smaller the ripple. But obviously, larger inductance and larger capacitor comes with the fact that we need larger space. It will take up more room on the board. So that would be a downside of it. In this case, I have this load that's constantly drawing 1 amp of current out of this switcher IC just to test how well this converter works under this condition. One thing to note regarding this output capacitor is the larger the output capacitor is, the less ripple you get. But another issue that arises is the fact that larger output capacitor corresponds to larger inrush current, because current that needs to get pumped into this capacitor to charge it up equals C times dV over dt. And because of that equation, the larger capacitance you get, the more current the capacitor is trying to sink out of this output, which leads to higher amplitude of inrush current. So again, that's another trade-off when it comes to minimizing ripple, but also maintaining the inrush current to a right value. And then feedback resistor, I explained that you need to follow this equation to get it to 5 volts. And then this 4.7 picofarads, this is for the op amp stability. So the feedback here basically connects to a comparator inside, which compares this output voltage to the internal reference. So if you go over 200 kilo ohm for R1, then we need to have a capacitor in here to ensure that we have a stable closed loop feedback. And then this pin here is RT. RT is basically a pin that sets the frequency, the switching frequency of this device. In this case, I have it set to 8.66 kilo ohms, which correspond to 1 megahertz. Again, depending on the application, you can select between hundreds of kilohertz to maybe 2 or 3 megahertz. A sweet spot for most applications is about 1 to 2 megahertz. Obviously, the faster the switching frequency, the higher the switching losses. With higher switching frequency, you can have smaller magnetics for the same amount of current. So when we switch the switcher at much higher frequency, like in this case, 1 megahertz compared to 100 kilohertz, it allows us to go to a smaller inductor while maintaining the same ripple performance and output current. And this TRSS is basically just the soft start. The idea of soft start is every time that this chip turns on, or every time this output gets triggered, we have a load that's sinking current out of this output pin. There is a small amount of ramp up or delay from when the chip is fully off to when the chip starts conducting, which we call it a soft start. And soft start basically helps a lot with the inrush current. So you guys recall I said that the larger the output capacitor is, the larger the amplitude of inrush current. But if we use a soft start feature, what soft start does is it ensures that the switch doesn't turn on as fast. It just introduces a little bit extra delay time for how fast the switch gets fully turned on. It introduces that ramp up, which helps with the inrush, because now you dampening how fast the rising edge of this inrush current can be. So in some cases, we are PWMing an LED or some sort of a load by switching this enable pin high and low. And switching this whole switcher on and off does create a lot of ringing, but introducing some soft start, in this case, following this equation, we can control how fast that turn on can be. It really depends on the application. But generally, you can omit this capacitor, this soft start capacitor, and what it does, it basically forces the chip to fully turn on and fully turn off without any delay. Obviously, there are going to be some delays because of the parasitics and because of the turn on of the actual FET, because the high side and low side MOSFETs have turn on time depending on how much charge they have at their gate. So it's never going to be instantaneous, but there won't be additional soft start ramp up time introduced to the switcher when you omit this particular capacitor. PG is basically just an open drain pin, which indicates power good. So if the regulated voltage on this node goes anywhere plus or minus 7% of the set value, in this case 5 volts. This power good pin basically latches low and it signals, this could be connected to a microcontroller, which signals a load to the GPIO pin on the microcontroller, and it can let the user or let you know as a designer that the regulated voltage now is not within range anymore. And then the mode and sync is basically a new feature that analog devices introduced. You could select between burst mode operation or pulse skipping operation. So burst mode operation is usually used in order to optimize performance of the switcher at small loads. So what that means is if we ground this particular pin, it would indicate that this chip is operating under burst mode operation, which what happens is at low load, when you have no load or when you have like milliamps of load, this switcher IC ensures that the IC consumes the absolutely minimum current. So it would make sure that the quiescent current that gets used again by this particular chip is absolutely minimum. So if that is a concern or if that's a consideration in your particular project or application, you should ground this pin, and that gives you the burst mode operation. So one quick note about why I'm using 2 capacitors in here. So the first capacitor basically is the capacitor tank. The reason that we have this is if the input supply is much further out from the IC, there may be some significant inductance because of the long wires or long cable. That's why we want to have the larger input capacitor, like 15 microfarad or like 20 microfarad, to ensure that low frequency, high impedance gets all snubbed using that bulk capacitance. And it's always good to group that capacitor with another lower capacitance, in this case 1 microfarad. You could also select a 100 nanofarad or something smaller to use as a decoupling cap. And this particular capacitor, as we're going to discuss in the next video for the layout design, it must be placed very close to the VN pin. And the reason for that is because this smaller capacitance sole role is to filter out all the higher frequency noise that may be present on the VN bus. So always ensure that the lower capacitance values are closest to the input pin, because they are the ones that are responsible for filtering out higher frequency noise before all that high frequency energy enters the chip. So now we need to run the simulation and see how it performs. So as you can see, the VN is our 12 volts, as I have it in here. And then we have a VOUT that is, again, because of the soft start capacitor that I selected, is ramping up from 0 basically volts all the way up to 5 volts. And as you can see, it's regulated within 5 volts. The soft start capacitor does not always predict the exact ramp up time. As I said, there will be some additional ramp up time that gets added to the soft start feature because of the turn on time of the high side and low side MOSFETs and other parasitics in the circuit. So one more thing to point out is on this plot for VOUT, we could also calculate the ripple of the output voltage. So if we just zoom in anywhere here on the steady state, you could see that obviously the output voltage is switching, hence being the switching regulator. And then here we get the actual ripple. And the way that we quantify the output ripple of buck converters is to measure the peak-to-peak voltage. And the way we do it is we can press on this VOUT, drag this guy right over here on one peak, and press it again, and get the second cursor, drag it all the way down to the second peak. And now what we get is the difference between the two. As you can see here, is shown that with this current configuration, with the current passives and magnetics, with the output capacitor and the output inductor, we find out that the output ripple is about 23 millivolts, which is pretty reasonable for a setup like that. Again, as we discussed, selecting a larger output capacitor decreases this ripple, but it'll contribute to higher inrush current and larger required space on the PCB. And that is it for today. I wanted to quickly talk about which switcher IC we selected for this 5 volt 1 amp buck converter, and just walk you guys through each pin functionalities and how we select all the passives around buck switcher IC and what are the trade-offs that we have to make when selecting the passives. In the next video, I'm going to talk about how to take the same exact circuit that we just simulated using LTSpice into an actual PCB in Altium. Thanks again, guys, for watching. Don't forget to drop a like, leave a comment, and subscribe. Let me know your thoughts in the comment section. Peace.